MATU 206, Week 8, Chapter 7. The word decimal comes from Latin decim, meaning 10. Just like if it was base 8, we call it octal, because oct means a prefix meaning 8. The decimal system has as its base the number 10, so decimal is base 10. We can represent the decimal system as follows, where we have the ones place, the tens place, which is the number of tens we may have, and then these the decimal point, and everything to the right of it is a portion of one, part of one. It's a fraction. So we have one group of 10, that's what this means, plus two groups of 1, plus 6 times a tenth, plus 1 times 1/100th, plus 8 times 1/1000th, plus 4 times 1/10,000th, plus 3 times 100,000ths. We read the number as 12. 1 and 2 makes 12. And that's what the decimal point says. 61,843 hundred thousandths. The 3 is in the hundred thousandths place, so that's why we give it that name. One thing about the word and, if somebody says 102 meaning this, what they really just said was 102. So the word and is very specific. It means the decimal point. Convert each of the following to decimals. Well, we have 10 in our denominator, so that means if the decimal point is there, this needs to end in the 10th place. So I put the final digit, the 5 goes there and the 2 goes there, and that is how I would convert that. 56 100ths. We have 100ths there, so the decimal point, that's the 10th place, that's the 100th place, so the final digit has to go in the 100th place, so I would put the 6 there, I would put the 5 there, and I like putting a 0 out in front of the decimal point just to protect it from being missed. Here we have 10 thousandths, so I put the decimal point there, tenths, hundredths, thousandths, 10 thousandths. So this is the 10 thousandths place. I put the last digit in the 10 thousandths place, so I have 502. I have to fill in the empty hole with a 2, and again I like putting a 0 out in front of the decimal point just to protect it. Convert each of the following to decimals. As you can see, there's a whole bunch of monkey business going on here. We have 7 in the numerator and 2 to the 6th power in the denominator. Well, what's happening here is we're going to multiply this 2 by something to try and get a base of 10. And the multiplication, the product rule kind of says that if we're multiplying things with the same denominator, we can pop that, or with the same exponent rather, sorry, we can pop that exponent out, and so we're kind of going the reverse of the that rule here, but it's the same thing. So we can, since we're multiplying two numbers with the same exponent, we can take that exponent out and then multiply the numbers, and we end up with 2 times 5 is 10, so we end up with 10 to the 6th. 10 to the 6th. And if we multiply the denominator by something, we have to multiply the numerator by the same value. And so we would expand 5 to the 6th out and get 15,625. Multiply that by 7 to get 109,375 in the numerator. And then we have 10 to the 6th, which is in the denominator. So that would bring us out into the tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths place, and 1, 2, 3, 4, 5, 6 places, and that's where we would then put our final digit is in that 6th place, and that's our conversion. Now here we have 1 in the numerator, and we have 2 to the third times 5 to the fourth in the denominator. So again, we want to try and manufacture this so we can have the something in the denominator that's a power of 10. And so what we're going to do is, we know 2 times 5 is 10, but we don't have the same exponent here, so we need to multiply by one more 2 in order to make 2 to the third times into 2 to the fourth. And so once we do that, if we're multiplying or adding in or multiplying the denominator by 2 to the first, we also have to multiply the numerator by 2 to the first, do the same thing. So that gives us 2 in the numerator, but now we have 2 times 5, and they both have the same exponent, so we can pull the exponent out, do the multiplication, 2 times 5 to the fourth, and then we need to have 4 places, 1, 2, 3, 4, and our digit will go into that final, the last place, and we have to fill the rest with zeros before the decimal point to give us our answer. Now we have 1 in the numerator and 125 in the denominator. We can realize that 125 is 5 cubed, and so we convert that into 5 cubed. And in order to get a power of 10 in the denominator, we would multiply 5 times 2. And so we have 5 cubed, though, so we need to multiply by 2 cubed. So we're multiplying the numerator and the denominator by 2 cubed, which leaves 2 cubed in the numerator, which gives us 2 times 2 times 2, which is 8. And now we have 10 cubed in the denominator. The exponent is 3, so we need 3 places, so the 8 will go into the tens, hundreds, thousands place. The last example here, we have 7 in the numerator, 250 in the denominator. I bet you we know that that's probably a power of 5 somehow or other. And it's 2 times 5 cubed. So we took a 2 out, divided a 2 out, and that left us 125. We need to then just multiply by 2 to the power of 2. 2 squared in order to get 2 cubed in the denominator, so we have the same exponent down there. 2 squared is 4, 4 times 7 is 28, gives us our numerator. We can pull that exponent out and do 2 times 5 cubed, so we have 10 cubed. The exponent is 3, so we need 3 places to divide by 3, and we will put the 8 in the final place, the 2, and so we have 28 thousandths. We have when we have decimals, remember they're all the real numbers, and on the left side we have rational and we have irrational. Our rational numbers, the smallest group of them are the natural numbers, and those are 1, 2, 3 as we would learn to count. The next classification up is the whole numbers, which includes all the natural numbers and the 0. The next group up is the integers, which includes all the natural numbers, the whole number 0, and then we have the opposite of the natural numbers, or the negative numbers. And then the top classification of rational numbers are fractions, or anything you can put into anything that looks like a ratio. We have terminating decimals, or we have repeating decimals, and those are the how we classify rational numbers. So we're looking at terminating decimals, and terminate means stop. So we're looking at decimals that stop. Decimals can be written with only a finite number of places to the right of the decimal point, are called terminating decimals, and they are terminating because they stop. They don't keep going on forever. They don't keep repeating or anything like that. A rational number, remember, it has the root word ratio in it, can be represented in a fraction form, a to b, can be written as a terminating decimal if and only if the prime factorization of the denominator contains no primes other than 2 or 5. So if we have a fraction, we need the denominator needs to be a base of 2 over 5, or a multiplication of those. Um, so these can be written as terminating decimals because 16 is 2 to the fourth. It's made up of a bunch of twos. 1940s can because it's made up of only twos, three of them, and a five. 160 has five twos and a five. So these can be written as terminating decimals because the denominators are only made up of factors of 2 and 5. These cannot be written as terminating decimals, 11/18ths, because if you factor 18 out, there is a 2 there, but it also has two threes involved, so it's going to not terminate. 526, 26 factors out to 2 times 13. Because of that 13, it will not terminate. And 84 is 2 squared times 3 times 7. Because of the 3 and the 7, it will not terminate. So to check to see if a fraction or a ratio will terminate, you perform the prime factorization of the denominator and see if it consists of only 2's and 5's. Ordering terminating decimals. The terminating decimal is easily located on a number line because it can be represented as a rational number in fraction form, and b is the power of 10. So if we're looking at 5600ths, because the 0, it will become between on the number line. It will become between 0 and 1. It's 5600ths is slightly larger than a half. So if that's a half, slightly less than 6/10, if we want to divide that up, and you can then locate it onto the number line. If we're going to compare terminating decimals, if we want to compare these two, we need to line them up by place value. And this is a pet peeve of mine because many of my colleagues in the math classrooms or elementary school teachers say line up the decimal. And while that's an easy thing to look for and an easy thing to remember, it's not getting across the concept that what we're really lining up is place value. So I might say, instead of line up the decimal point, I might say line up the ones place. So, and then I would tell the students, how do we know where the ones place is? And they can tell me it's the place to the left of the decimal point. Still gets this idea of lining up the decimal point in there, but it focuses more on place value, which is the importance of what we're lining up. So once we line up the ones place, then I will start comparing, going from the greater side to the lesser value. And so the zeros are the same, the sixes are the same, the sevens are the same. We have a difference here. This is larger than this, so this value on top would go to the right of the value on the bottom on the number line. But again, I have a pet peeve about people telling students to line up the decimal. It's easy, it's understandable, but it's missing the concept of what we're really doing here. Adding decimals, we can make them into pictures, pictorials. This is more in the primary grades where we have two sets. Yes, there's one line there and there's one line on the back of it of hundreds, and that's a 10 by 10 grid. And then we have one of those lines that is 1/10 of a whole, and we have 6 of these blocks then, because 6 of them, since this is hundredths, we take 6 of those blocks for 600ths. And we have then one of those 100 blocks and 7 of the columns and 3 of the blocks, because we're talking about hundredths place. So in order to represent decimals of hundredths, we have to make one whole equal 100 of those little blocks. We can change the problem to one we've already know how to solve, that is to a sum involving fractions, if you want to show students how decimals relate to fractions, which I would appreciate, where we have 2 plus 1/10 plus 6/100 and 1 plus 7/10 plus 3/100. So then we can add the 6/100 and the 3/100 and have 9/100. We can add the 7/10 and the 1/10 and get 8/10. We can add the 1 and the 2 and get 3, and then we can combine them back into a decimal number. And all this is just to help students get the concept of how fractions and decimals relate. So often I end up with students, the majority of my students when they arrive in my classroom, middle school students, say they hate fractions. Fractions are hard. They can't do fractions. And yet, pretty much by the end of the year, most of them don't mind fractions because that's probably what I live in most of the year. And I don't do much with decimals. And students want to always convert the fractions to decimals, so I make them really untenable fractions to do that with, and so they learn that fractions are easier or not all that difficult, and I prefer fractions because they're exact numbers. Frequently when you change a fraction into a decimal, you introduce error. Multiplying decimals, if there are n digits to the right of the decimal point in one number and m digits to the right of the decimal point in the second number, multiply the two numbers ignoring the decimals, and then place the decimal point so that there are m plus n digits to the right of the decimal point. One of the problems that if you're showing students how to multiply decimals after you've shown them how to add decimals, what they'll try to do is line up the decimal points instead of lining up the place value, and they will just then bring the decimal point straight down rather than understanding that what we're really talking about is place value and not worrying about the decimal point. So you have to make sure that they're counting the number of digits to the right in both of the factors and then bringing it over the sum of those two values. So compute each of the following. We have 1 and 43/100 times 6 and 2/10. So we would have 6, 8, and 2. We have 18, carry the extra group of 10, 24, 25. I write the 5 down and I carry the two groups of 100 over there, and I have a 3 and 6, 16, 5, 6, 7, 8, and 3. Now I always show my students, okay, how many digits to the right? 2, and I put the arrow there and I do this, and even though they can do it in their head, and then I put together an addition problem and show them 3, and that's how many we're going to bring over. So 1, 2, 3. Oh, I also ask students, where does the decimal point hide? And I want them to realize that if there's no decimal point visible in a value, the decimal point is there and it's hiding to the far right end. So then we have 13 thousandths times 2/100. So that's 6 and a 2, and all the rest is a bunch of zeros. So here I go again. How many digits? 0 is a digit, so there's 3. How many digits to the right is 2. What's the sum is 5. Where does the decimal point hide? Right here, but I have to move it 5 to the left. So 1, 2, 3, 4, 5. And yes, I have them draw the little loop-de-loops because now they have to fill in the empty holes. And I also put a 0 out in front of the decimal point, and that's tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, so we have 2600 thousandths. Scientific notation. Scientific notation can be a scary prospect, but it really isn't. What we need to know about scientific notation is that in scientific notation, it's all about the decimal point, and that we can only have one digit to the left. Only one digit to the left. for scientific notation. We can have lots of digits to the right, but for true scientific notation, we can only have one digit to the left, and then we're multiplying by a power of 10. So, for example, the distance light travels in 1 year is a really big number starting with a 5, and it's called a light year, and we express it by 5 and 872 thousandths times 10 to the 12th. That's because the decimal point then has to go at this point right here, because we can only have one digit to the left of the decimal point in scientific notation. The decimal point's hiding here. How many places did I move it to the left? I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I moved it 12 places to the left. So this number here is really times 10 to the 0. I put the decimal point there, and I made this part of the number smaller, so I have to make this part of the number larger, and so that's why I'm adding 12 to that 0, and I end up with this. The mass of an electron is this really small number, and again, I want to change it into scientific notation. I need one digit, a real digit other than 0, to the left. So that means the decimal point is going to go there. Oh, and yes, since this is standard form right now, it's times 10 to the 0. So I need to move the decimal point 1, 2, 3, 4 places so that I get 5.4875 times 10. I made this part smaller, so oh no, I made this larger, sorry, forgive me. Made it larger, so I have to make this value smaller, so I made it larger by moving the decimal point 4. So since I have to make this one smaller, I'm going to subtract 4. 0 minus 4 is a negative 4. In scientific notation, a positive number is written as a product of a number greater than or equal to 1 and less than 10. That means it's greater than or equal to 1 and less than 10. That's where it comes the one digit to the left of the decimal point, and an integer power of 10. To write a negative number, you treat the number part as a positive number, but we put a negative sign in front of the result. So how do we change all these into scientific notation? Currently, this value is times 10 to the 0. I need to get the decimal point to there, so I will have 4.13682. How many places did I have to move the decimal point? 1, 2, 3, 4, 5, 6, 7, 8. I moved it 8 places to the left, making this part smaller, which means I have to make this part larger. And so I'm going to I moved it 8, so I'm going to add the 8 to there, so that's times 10 to the 8th. How do I deal with this one? Well, this one I start out, it is times 10 to the 0 power, because it's in standard form. I need to get to the decimal point to there. So I have 1, 2, 3, 4, 5. I move it 5 places to the right, so that I end up with 2 and 31 hundredths. And now that's times 10 to the something. Well, I made this part larger, so I have to make this part smaller, which means, and I went to the right, so I have to subtract my 5, so I have times 10 to the negative 5. Doesn't mean that this value is negative. This just means that I'm moving the decimal 5 places to the right, or that I moved it. These negatives and positives in front of the exponents are really just directional as to which way the decimal point's moving. 83.7, and that's times 10 to the 0. I need to have it there, so I'm moving it 1, so that I end up with 8.37 times 10. I made this side smaller, so I'm going to make this side larger, which means I'm adding, so that's times 10 to the first. Now here I have a negative sign. I'm going to put my negative sign over here in front of the answer, and then work with this as if it was positive. The decimal point's hiding here. I need to get it there, so I'm going to have 7 places I moved it that way, and I end up with 1.0, so that's just 1 times 10. This was times 10 to the 0. I made this side smaller, So this side has to be larger, so I'm I'm adding 7, so that's times 10 to the 7th. Now I want to convert back to standard. Um, so what I need to do is notice that I want to turn this into something times 10 to the 0. So what do I have to do? I have to it will be moving it 5. I'm making this side larger. So this side I need to make smaller. Which way do I move the decimal point to make this side smaller? I move it to the left, and I need to move it 5 places. 1, 2, 3, 4, 5, and that's where it will be. So I'll have 0 point. I have 1, 2, 3, 4 empty places. 1, 2, 3, 4, and then 6, 8, 4, and that's standard notation because that comes out to be times 10 to the 0, which we typically don't write. I have 3.12 times 10 to the 7th. I want to make this times 10 to the 0, which means I'm going to make this side smaller, which means I need to make this side larger. Which way do I move the decimal point to make it a number larger? I move it to the right, and I'm going to move it 7 places. So I have 3.12, which will make 1, 2, 3, 4, 5, 6, 7, and fill all these holes with zeros. And so I'll have 31,200,000. Again, here I have this negative out there. I kind of ignore it because I just put my negative, because this scientific notation doesn't have anything to do with being positive or negative in and of itself, and it just makes it complex, so I'll just leave it there. I want to make this times 10 to the 0, which means I'm making this side smaller, which means I need to make this side larger, which means I need to move the decimal point to the right 4 places. So 4, 0, 8, 1, 2, 0, 0, 1, 2, 3, 4. So I have a negative 40,800. Dividing decimals. The problem with dividing decimals is that we have to worry about what to do with the decimal point. One option of that is to change the decimal value into a fraction, which we can do by multiplying. And what we can do is if we put it over 10, that means we can get rid of that decimal point. But then the problem is that the divisibility rule of for 4 being able to divide evenly doesn't work because the last 2 digits, 86, is not evenly divisible by 4. So then what we can do is if we multiply by another 100, 60 is divisible by 4. So that's what's going on here as to why we are now worrying about dividing 112 or 12,860 by 4 instead of 128 and 6/10 by 4. So when we do that, we can divide by 4 over 1, but then we want to divide by 4, so we want 128,000 or 12,860 divided by 4, but we have to multiply that by the 1/100th, and that's where that fits in. We can go ahead and do this division without the decimal, but then we need to put the decimal point back, which when we multiply by 1/100th, we do. Typically, we don't worry about that concept there, but we just divide 128.6. We put that inside and divide by 4. We just move the decimal point straight up and go through division. When the divisor is not a whole number, as in dividing by 32 hundredths, we do want to make this into a whole number so we can divide by it. And so then we move the decimal point over 2 places, and then we get that division problem. In elementary school textbooks, this process is usually described as, yes, as I just said, moving the decimal point 2 places to the right in both portions of the number. But what we're really doing is changing both of we're changing that into a whole number by multiplying by 100, and if we multiply this by 100, we have to multiply that by 100 also. Mental computation. There are several ways of being able to add or numbers mentally. One is called breaking and bridging, where what we do is if we have 1.5 plus 3.7 plus 4.48, if we take that 3 and add it to the 1, well, then we get 4.5 plus 7/10, which we can then typically do in our heads and get 5.2. And then again, we take the 4 and add it to the 5, the whole number part, so we have 9.2 plus 48 hundredths. And we can then add the 2/10 and the 4/10 and get 6, so we have 9 and 68 hundredths. It's just a way of breaking things up, so we're only adding one number at a time, and hopefully makes it easier to do mentally. We can use compatible numbers, in other words, putting together numbers that make a better value. So if I see 3 and 85 hundredths and I see 15 hundredths, I know I can put those two together to get a 4, and I know I can put the 9 hundredths together with the 91 hundredths and get us another 1, which makes that 8, and 4 makes 12, so then 12 plus 4 is 16. We can go ahead and make compatible numbers if they aren't already there, because I know 3.79, if I take 4 off it, and I take 2 off the 0.27, I can hold those over there. I know then that 20, that makes a whole number 1, so I can 9, 10, 11, 12, 13, but then I have to add that what I had added or subtracted off, moved aside to be able to get back together. Balancing with decimals and subtraction. Again, in order to subtract, if I take and add 3 to this 1 and 97 hundredths, I know I changed it into a 2, and I would it's easier to subtract 2 than other things, so the number I'm subtracting, if I can make it into a whole number, I'll do that, and I can do that by adding 3 hundredths, and if I add 3 hundredths to this number that I'm taking away, I have to add 3 hundredths also to the other number that I'm keeping, so this is where 3 hundredths minus 3 hundredths is 0, so I'm not really adding anything to the number in order to get a whole number that makes it easier to subtract. Balancing with decimals and division. If I'm dividing, I know that is a quarter, so if I multiply by 4, I'm now going to be dividing by 1, and I love to divide by 1 because it's really easy. And so, but if I multiply the divisor, I have to multiply both parts of the problem by the same value. Now we get to round each of the following numbers. The first thing I need to do is I'm going to the nearest hundredths place, so I have to establish which one is the hundredths, tenths, hundredths. So that's the hundredths place. In order to round, I look to the digit just immediately to the right, and if it's 5 or more, I add 1. If it's not, I don't. So 6 is 5 or more, so I'm going to add 1 there and throw everything away there, so I end up with 7 and 46 hundredths. Here I'm rounding to the 10th place, so that's the 10th place. I look next door, I see it's a 5 or more. I add 1 and I throw all that away, so I end up with 7 and 5/10. To the nearest unit, or the ones place, there's the ones place. I look next door, it's a 4, it's not 5 or more, so I'm adding 0, I'm adding nothing, and I throw all that away, so I end up with 7. Now I'm rounding to the nearest thousand place, that's the 1,000. I look next door. That's not 5, so I'm adding 0, and I'm changing all those into zeros, so I end up with 7,000. I'm rounding to the nearest 10. Whoops, that's the ones place. I round to the nearest 10. I look next door. That is 5 or more, so I'm adding 1, and I'm changing that to a 0, so I end up with 750. I'm rounding to the nearest 10. I look next door, that's not 5 or more, so I'm adding 0, I'm making that 0, and I can throw the fraction part away, so I end up with 70. Estimating decimal computations using rounding. Rounded numbers can be useful for estimating. When computations are formed with rounded numbers, the results may be significantly different from the actual answer. When we estimate, when we round, we frequently put in error, so be aware of that. that when rounding can cause error. It all depends on how accurate you need to be as to whether or not that error will be a problem. Round-off errors are typically compounded when computations are involved. So if we have two numbers and then round them and then do a computation or an operation with those numbers, the errors may increase. And so when computations are done with approximate numbers, the final result should not be reported using more decimal places than the number used with the fewest decimal places. So if it's 3.85 times 2.7, and I round so that I round both of them, so I have 3.9 times 3. I can't put my answer and have more than one decimal place. So the least accurate number to find it. So non-zero digits are always significant. Zeros before other digits are non-significant, so a zero in front of those two digits, that's not significant. Zeros between non-zero digits, that is significant because you have no tens there. Zeros to the right of the decimal point are significant if you have a whole number off there. And to avoid uncertainty, zeros at the end of a number are significant only if to the right of a decimal point. We talked earlier about terminating decimals, decimals that stop. Now we're talking about repeating decimals, or decimal numbers in a pattern, so that they form a pattern and repeat. For example, if we convert 2/11ths into a decimal using long division, uh, we'll notice that we get a repeating pattern of the 18, 18, 18, 18, 18, and that will keep going forever. So that's called a repeating decimal. A decimal of this type is called and the repeating block of digits is called a repeatend, although I've never heard that used in real life. Oh well. And the repeating decimal is written with a bar over the repeating portion, over the block of digits that are repeating. So convert the following to decimals. This fraction bar says divided by, so I tell the students the top goes in, the bottom stays out. We have to add a decimal point and several zeros, bring the decimal point up. 7 will not go into 1. 7 goes into 10 one time. 1 times 7 is 7, and we do the subtraction and we get 3. We bring down the next digit. 7 goes into 30 4 times. 4 times 7 is 28, and we have a 2, and we bring down a 2. 7 fits into 20 2 times. 2 times 7 is 14, and we have a 6. Wonder how far you want to go. We bring down the next 0. 7 goes into 68 times, which is 56, and we do the subtraction to get 4, bring down another 0. 7 fits into 40 5 times, which is 35, and we have a 5, and bring down another 0. 7 fits in there 7 times, which is 49, which is 1 and a 0, and 7 goes in there 1 time, which is 7, and a 3, and bring it down to 30, and it appears like I'm starting to repeat myself, because now 7 goes in there 4 times, and which is 28 and 2, and I'm repeating myself, so this block right here repeats. I do know that when any number with a 7 in the denominator will have 6 digits repeating. How do I turn this? Well, again, I draw the division box. The top goes in, the bottom stays out. I add a decimal point, a bunch of zeros. 13 will not go into 2. It goes into 20 one time, which is 7 and 0. It won't go more than 7 times. I'm going to guess maybe about 5 times. 15, 5, 6. So there's 5 times, and 65 makes 5 and a 0. And maybe about 3 times, which is 9 and 39. So there's 3 times, which is 39, which gives us 11, and bring down the 0. And maybe about 8 times, which is a 60. And then it goes in there 4 times, which is 52, and 8, and bring down a 0. And I think I'm supposed to keep going until it repeats. I wonder when it will repeat. Um, Looks like about 6 times, which will be 13 times 6, which is 18, 78. 78, which is a 2. Oh, there I am. I have my 2 again. And so it's going to be, that's the repeating part. Writing a repeating decimal in the form of a fraction. So if we have a repeating decimal in the form of a fraction, there is a routine for finding this, especially if the repeating block is right up against the decimal point. Then it's fairly easy. The first thing we do is we say, well, let x equal that repeating decimal, and it keeps going forever. What we want to do is find a way of getting rid of the repeating part and making it cancel out. So there is 1 digit repeating here, so I'm going to multiply both sides of this by a 10. So that means 10 times x is 10x, and here when I multiply by 10, I'm moving the decimal 1 point that way, so it's so forth and so on, repeating. And then I can do 10x equals 5 and 5 repeating, minus the x and 0.5 repeating. And 10x's minus 1x leaves a 9x. And on this side, the repeating parts cancel out, which leaves a 5. And then I want only 1x, so I can divide both sides by 9. And so x equals 5/9. As you do several of these problems, you'll start seeing a pattern emerge, which is what I work on with my middle school students, that if there's 1 digit repeating, the denominator is going to be a 9. If there's 2 digits repeating, the denominator is going to be a 99. And so if we had something like x equals 0.378, 3 digits repeating, what it's going to end up being is 378. 3 digits repeating, there's going to be 3 9s in the denominator. And so that is the fraction representation until I can realize that 3 plus 7 plus 8 has a 3 in it, and there's 3's in there, so I can reduce that. So I better reduce it. So the numerator is 1, 2, and 6, and the denominator is 333 then, and there's still a 3 in the numerator, so that's 42 and 111. So that's the quick way of doing it, but then you do have to still reduce the fraction. So there is a pattern when the repeating part is right smack dab against the decimal point, then it's the repeating part in the numerator, and the number of digits repeating goes in the turns into 9s in the denominator, and then you reduce. There is a problem though that you do still have to go through this type of process if the repeating part isn't right against the decimal. So if we want to change 2 and 345 with the 45 part repeating into a ratio or a fraction, the one thing we need to do is move this decimal here so that the repeating part is up against the decimal point. So if n is equal to 2.3 with 45 repeating, we multiply both sides, that moves the decimal point. So we have 45 repeating. But now here's the part we're going to use, and what we need to do is, in order to get this disappeared. There's 2 digits that are repeating, so now we want to multiply both sides by 100. So we have 100 times 10 times n is equal to 2, 3 multiplying by 100, so I have 45 with 45 repeating. Then I can take this becomes 1000n is equal to 2345 with 45 repeating, and I can subtract this part, so I'm subtracting 10n equals 23 and 45 repeating, which now the repeating part goes away. 5 minus 3 is 2, 4 minus is 2, 3 and 2, and I have 990n, and so I divide both sides by 990, and n is equal to that fraction, but I'd have to reduce it and end up with that. In order to put repeating decimals into order, you still line up the place values and still compare. It's just that if we're lining up I can't just add zeros. I have to keep going and start repeating. So I rewrote the 3 and the 4 here as the part repeating so I can fill in. And so then that's the same, that's the same, that's the same, that's the same, that's the same. Oh, there's my difference. 3 is bigger, so that one's a larger number. Now, can I find a rational number in decimal form between these two values? I'm looking for something that comes between them, and so I line them up, and I see there's where the difference is, so I can put a 0.352 because 2 comes between 3 and 1 as my value that comes between. And there's infinitely many others because I can have 0.35 to 1, to 2, to 3, to 4, 2 to 5. Any of the, carrying that part down, any of these will come between. Percents. Percents are special kinds of fractions because they have a denominator of 100. The word percent is another Latin phrase, per centum or per 100. Definition of a percent is any value with the percent sign is equal to that value divided by 100. Okay, converting percents. 100% means you have the whole thing, the 1. So to go this way, you drop the percent sign and move the decimal point to the left. So going from a percent to a whole number, you move left and drop the percent sign. Going the other way, you move the decimal point 2 places to the right, add zeros, and add the percent sign. So here we would do this, and here, and here, and here we would still have, here we do this, so a 1 is 100%. This we do have to convert, or we could multiply by something to get us to 100, but this is the most straightforward way. And when we divide this, we get a 6 repeating, so then we would have 66 and 6 repeating percent. Write each of the following as a decimal. We drop the percent sign and go 1, 2 places, so we drop the percent sign and go 1, 2, so we drop the percent sign and go 2 places. We drop the percent sign and go 2 places. This is 66.6 repeating percent, so we drop that and go 2 places, so that's still just there. And 33 1/3 is 33.3 repeating, so we move the decimal point, so we have 0.333 repeating, or just 0.3. Want to address this, that in real life we use percentages above 100, but mathematically speaking that's an impossibility, because how 100% means everything, and how can you have higher than everything? Applications involving percent. Applications involving percent usually fall into, we're usually finding a percent of a number where we will multiply. We find what percent one number is of another, which is usually a division process, and find a number when a percent of that number is known. So if you know that 42 is 60% of what number? So a house sells for $92,000, requires a 20% down payment. What is the amount of the down payment? We're trying to find 20% of 92,000, and so that is a multiplication problem. You change the percent into a decimal and multiply. If Alberto has 45 correct answers on an 80 question test, what percent of his answers are correct? This is a division where you put the number known out of the on top and the total possible on the bottom, and you will do the division and then change it, multiply by 100 to change it into a percent. And 42% of the parents at the school, children in Paxton School District are employed. We know 42%, and we know the number of parents used at the university is 168. So 168 is 42% of what number? And so that's a multiplication there. So 168 is equal to 0.42x. And in order to do this, then we divide both sides by that and find out that that would be our answer. Kelly bought a bicycle and a year later sold it for 20% less than what she paid for it. If she sold the bike for 144, what did she pay for it? We're looking for the original price. So we have $144 is how much she sold it, and the original price minus what she lost. As they say, here's Kelly's loss, and Kelly's loss is 20% of P, so we know that P minus 20% is that, and so it works out to be $180. Westerners clothing store advertises a suit for 10% off for a savings of $15. Later, the manager marks the suit at 30% off the original price. What is the amount of the current discount? 10% discount amounts to a $15 savings. We could find the amount if we knew the original price. P, the original price was $150. So 10% of what is $15? So that's 0.1 times x equals 15. So then we have to divide both sides by 0.1, and we find out that x is $150. That gives that. So now to find the current discount, we will take that $150 original price and multiply that by 30% to find out that later on to 30% off the original price. So we find out that that's $45, and to find out the new cost, we have to do the subtraction to find out that the suit is now $105. Mental math with percents. We can use fraction equivalents. 1/4 is 25, half is 50%, 3/4, 1/3, 2/3, 10 1/10 is 10%, 1/100th is 1%. So what we usually do is use a known percent. We may not know that to find 55% of 62, we can find half of 62 and find half of 6.2, because I know 5% I is move the decimal point and move the decimal point. Laura wants to buy a blouse, which was originally at $26.50, but is now on sale at 40% off. She has $17. Can she afford it? So what we're looking for is times 0.4. Well, I might be able to say that I would be able to use in my head that 20% or 40% of 25 is 4 times 10%. So I'm going to kind of estimate that. Or if I was doing this, I would say, okay, 10% of that is 265, but I know that it's 4 times, and so I'm going to, I would probably round and say 270, because then I can have, that's 280, that part, and that is 8, and so I know that it's about 1080 off, and I have to do then the subtraction, and 16, about 15, so I would say that $17 does have enough cash. It's all you can work your numbers. Which of the following statements could be true and which are false? Leonardo got a 10% raise at the end of the first year on the job and a 10% raise after another year, so his total raise was 20% of his original salary. That's false, because if his original salary was $1,000 and he got a 10% raise, that means 10 times 10%, that means, which is 100, that means his new salary is 1,000 plus that percent raise is 1,100, and then he got a 10% raise again, that is equal to 110. So now his new salary is 1,210. It's not, and that's not 20%, because 20% is 200. These two people paid 45% of their first department store bill of $620 and 48% of the second department still. They paid 45 plus 48, 93% of the bill. No, they didn't pay 93%. You can't just add percentages like that, because the 45% takes a chunk of it away. So 45% of 620 would be roughly half of 310, but then they paid 48%, another roughly excuse me, half of that, so they would be about 155, so they would have paid about 465, which is not 93% of 1,000. Bill spent 25% of his salary on food and 40% on his housing, so since it's taking out, yeah, you can add those together, because if his salary is $1,000, he spent 25% on that, which is $250, and his salary is $1,000, and he spent 40% on that, which is $400. You add those two amounts together, and you get $650, which is 65% of his salary. Go ahead and give that one a try. Computing interest. When you borrow money, you have to pay somebody for the right to use it, and that's where interest comes. Is this you're paying them for the use of their money, or if you put money into a bank, the bank will pay you a little bit for the use of your money. We have terms that the amount that's either borrowed or put in is called the principal. The 5% is the rate of interest, and the time period or number of years, and interest rates are usually in years, is the amount of time. Now, simple interest means just the percentage is on the amount for the entire time. It doesn't compound, which we'll look at next. So the formula for simple interest is the amount of interest is the amount of the principal times the rate times the duration, or the time. So Vera opened a savings account that pays simple interest rate of 5 1/4 per year. So she's going to make 5.25% each year. If she deposits $2,000 and makes no other deposits, um, find the interest and the final amount for 90 days. So what we do is we take the 2,000, we have to multiply it by the rate, and then we're doing 90 divided by 365 because it's not an entire year, and interest usually is based on a year. So then what we'll do is we'll multiply these two values. We can multiply it by 90 and then divide by 365. So we'll find out that her interest is $25.89. Find the annual interest rate if a principal of $10,000 increased to 10,900 at the end of the year. So we're looking for the rate. We is an increase, so we're finding a difference. So the amount of interest was $900. So our percent of 10,000 equals 900, and let's see, interest is equal to the principal times rate times time. The time is 1 year, so that kind of goes away. We don't know the rate, but we're dividing the interest by the principal to find out what the rate is. Compound interest. That's when interest is paid on the money every period or every so often. Usually, frequently it's done once a year, which is done annually. So you have money in the bank, and every year the interest is deposited, and so then the next year you're getting interest on the amount of money you have in there plus the interest from the previous year. Or it can be semi-annually, so every 6 months, or quarterly for every 4 times a year, every 3 months, or it could be monthly, 12 times a year, or if you're lucky you can find compound interest that's paid daily. Um, it's even if it's compounded, you're giving an annual, and that's usually an annual percentage rate is what they'll call it. And so the APR is not equal to the current rate because it's being compounded. If you invest $100 at 8% annual interest compounded quarterly, how much will you have in the account after a year? So it's 8%, but that means every quarter, because you're being paid quarterly, you're actually making 2% a quarter. And what this chart means is that for the first period, or for the first 3 months, if your initial amount is $100, what you'll end up with is 100 times that 100 times the 2% interest. And now the second quarter, this is the amount you start with there, and again that amount you started with, which in the first quarter was 100, but now it's this, is also multiplied by 1.02, or you have 1.02 times 1.02, or 1.02 squared times 100. And now that's your starting point for the third quarter. So this is how much money you start out in the third quarter, and you're making that much interest, which when you multiply these two together, you get 1 and 2 hundredths cubed times 100, because this 100 just kind of carries through. And so by the end, what you're actually getting is 100, the original amount, times 1.02 to the fourth. And if we do this math, what that means is 1.02 times 1.02, get that amount, and then times that by 1.02, get that amount, and times that by 1.02. What you'll end up with is 108.24. So you would make up, if it was straight 8% simple interest, you would end up with $108. But you're making a little bit more because it's compounded, and you're making interest on the interest is why it's more. The formula for computing interest, the amount of at the end of the nth compound interest period is where the amount is equal to the principal, the amount you started with, times 1, which we saw in that chart. The 1 is there, plus the rate to the nth power, or the number of periods that they're there are. That previous one was quarterly, so that's why we ended up with a 4 there. So suppose you deposit $1,000 in a savings account that pays 6% annual interest compounded quarterly. So we're looking at quarterly. We put in the amount is going to be 1,000. There's our initial value. The 1 is part of the formula, plus the 6% is changed into decimal, so 0.06, and it's quarterly, so that's divided by 4. In the previous example, we had 8 divided by 4, which is why it came out to be, or 0.08, why it came out to be a nice 0.02, but here we're not doing that, so we have to show the divide by 4. We add those together, we multiply this together by itself 4 times, and then multiply by the 1,000 to get the amount. The effective annual yield on this investment is what it would, if it was simple interest rate, what would we have here? You've got to find the amount of interest earned, which is this amount up here minus the original deposit, and then you can work backwards by taking that in as the amount of interest. So 6.136 is equal to the principal was 1,000 and the year was 1. So the annual percentage rate is 6.136%. That's how that's calculated. So you're doing better than 6%. Save for their child's college education, a couple deposit $3,000 into an account that pays 7% annual interest compounded daily, so it's 365. Find the amount of this account after 8 years. So we take the 3,000 and put it in for the that. We change the 7% into a decimal, so we have 0.07, but it's daily, so we divide that by 365. But then the period is 8 years, which is the 8, but it's compounded daily, so we have to multiply those. 8 times 365 becomes our exponent, which is a really big number. Wouldn't want to do that in my head. Couldn't do it in my head. And when we work all that out, we'll find out that. So really you just need to know where to plug things into this formula.